Welcome to the Blueprint Atlas. For half a century, global defense contractors have poured billions into a singular obsession. They sought to create the perfect armor, leading to the invention of modern Kevlar. We even synthesized ultra-high molecular weight polyethylene to stop high-velocity, lethal ballistic projectiles. Yet, when subjected to extreme kinetic energy, our greatest materials shatter or melt completely.
They transfer so much blunt force trauma that the armor becomes as lethal as the bullet. Our best engineering fails, revealing we have hit the ultimate chemical limits of humanity.
Every defense contractor faces a devastating truth. Human technology is stuck in a deadlock.
The military-industrial complex remains powerless to solve this fundamental, high-stakes material crisis. And now, we must look outside our sterile laboratories for an evolutionary answer.
But less than 1,000 miles from these failing laboratories, a miracle of biology exists.
A blind, brainless biomechanical drone effortlessly manufactures a material that humiliates human engineering.
It spins a golden filament so advanced, it leaves material scientists paralyzed in technological envy. To the average person, this golden web is a minor nuisance to brush away.
But to a defense contractor, it represents the holy grail of physical materials science. Observe this natural masterpiece, the Golden Orb Weaver's highly efficient, energy-dissipating factory.
We are not looking at a web. We are reverse engineering a military-grade mega-project. Let us evaluate the structural integrity of this unparalleled biological armor at a molecular level.
To measure strength, engineers look at tensile stress, calculated by force divided by area.
Industrial alloy steel can withstand immense stress before fracturing, but it is incredibly heavy.
Kevlar is lighter, but it completely lacks the elasticity needed to survive extreme impact. The dragline silk of the Golden Orb Weaver shatters the fundamental rules of materials science. It possesses tensile strength comparable to high-grade steel, combined with unbelievable physical flexibility.
This miraculous biomaterial can stretch up to 40% of its length without breaking.
How is this possible? The secret lies deep within its microscopic nanoscale composite structure. At the nanoscale, we discover rigid, geometric beta-sheet nanocrystals, providing extreme stopping power.
These hard nanocrystals are embedded within an amorphous protein matrix, acting like highly engineered springs. Together, they dissipate immense kinetic forces, leaving human-made synthetic polymers completely obsolete.
This hybrid molecular blueprint represents the pinnacle of structural efficiency and impact resistance.
No human laboratory has ever replicated this level of molecular organization and strength. The blue protein strands absorb the rest of the physical energy, acting as highly efficient microscopic rubber shock absorbers. Imagine weaving a dragline spider web where threads are the thickness of a pencil.
That scaled-up web would possess enough tensile strength and kinetic absorption to stop a jet.
It could catch a fully loaded Boeing 747 jumbo jet, flying at its cruising speed.
The aircraft would halt in midair without snapping a single golden thread of silk.
The kinetic energy absorption is mathematically staggering, dissipating millions of joules of violent energy. Nature achieves this unbelievable feat with a structure that remains lighter than organic cotton. This brings us to the impossible problem driving human synthetic chemists completely mad.
To manufacture Kevlar, human engineers require extreme, highly hazardous, and violent environments.
We must dissolve toxic polymers in concentrated sulfuric acid, boiling them at high temperatures. The extrusion occurs under immense pressure, making it toxic, energy-intensive, and incredibly inefficient.
Now, observe the spider. It possesses no blast furnaces, nor does it use acid. Its only raw materials are simple water and digested insects found in the forest.
At standard atmospheric pressure and ambient temperature, it processes an aqueous liquid protein soup.
It instantly extrudes it into a solid, bulletproof fiber via natural shear forces alone.
Humanity's desperation to steal this genetic blueprint reached absurd heights in the early 2000s.
Realizing we could not build a machine, we tried to hack biology itself.
Bioengineers successfully spliced the spider's DNA into the genome of dairy goats.
We attempted to milk the bulletproof proteins directly out of the goat's udders.
The legendary spider goats were real, but human extraction ruined the delicate molecular folding.
The resulting fiber was weak, brittle, and entirely useless. Evolution easily outsmarted us.
The ultimate secret of this mega project lies deep inside the spider's microscopic spinneret. This is not a simple nozzle. It is the most advanced 3D bioprinter. By manipulating pH levels and ion concentrations, the spider alters thread properties in real time.
It can print sticky silk for traps, or rigid structural cables for scaffolding.
It dynamically engineers bespoke metamaterials on the fly with absolute biological perfection. We look at our jets, our armor, and our skyscrapers with immense human pride. But the Golden Orb Weaver is a brutal, humbling reminder of our chemical limitations. We cannot copy it. The ultimate armor is currently catching flies in the woods.
Next, we examine termites constructing mud skyscrapers that perfectly regulate temperature without electricity. Click the video to discover the self-cooling alien cities we are desperately trying to copy.